Well, today I'm going to talk about 3D printing and the design freedoms it offers to the manufacturing industry. And we'll look at a different range of applications where 3D printing can actually make a real difference to what we see around us. But before we get into all that, let's look at this very nicely set dining room and all the objects inside it. We've got a plastic set of chairs which are slightly different in design, have very nice curves on them, but provide very critical functions which are to support someone's weight. I suppose there's perhaps a weight limit to some of these designs, but they should still work, hopefully. We've got wonderful wood construction there, straight lines, nice curves, some ornaments on a wonderful wooden frame there with the mirror on it. And all these are different materials, different designs, all based on fairly simple constructs of straight lines and simple curves. But if you look at this and you think, well, is that really all there is to it? I mean, most of these objects are actually just fully solid in certain sections, and is that how everything is? Is that what we might see around us? And there's some wonderful things on stage here as well that kind of illustrate this point. Well, the answer to these limitations in terms of the design is actually in the manufacture. If we look at what a carpenter has to do, he has a block of wood, or essentially uses wood as his material of choice to create very wonderful things. They could be large objects like the chairs we were looking at. They could be more intricate designs in terms of ornaments, in terms of what we were looking at in that mirror frame. We've got some good examples of window frames here, which are quite large in structure. And if we looked at the tools that are used to kind of wield this material, they can range in terms of sizes. We can have chisels for small, precise work. We can have saws for much larger work. The same applies if we were to work with metals, for example. We can cast metal, so we pour liquid metal into a mold. Or alternatively, we can mill metal, so we can take a block of metal and actually curve a shape into it. And that creates a broad range of things and products that we see around us. The same applies to plastic, so we just saw some wonderful plastic chairs, and they'd be created through using molds. Again, you put the liquid plastic in and you let it set, and out comes a chair. But what if there was a manufacturing process that didn't have some of these limitations? For example, most of what you can create with these current materials is actually fairly solid objects. And I'll get to the reason I keep mentioning solid objects. There's actually a point to it, which we'll get to later on. But what if there was another way of doing this? Something that offered perhaps greater design freedom. As a designer, you would never design something for wood or for metal or for plastic that could never actually be built. You'd focus your design work on what can be built. Well, 3D printing is another manufacturing method. It's fairly, well, some may argue it's fairly new, some may say it's actually quite old. It's about perhaps 20 years old. It works, as you would have seen in Larry Sass's talk, works by manufacturing through creating layers of an object and building those layers up until you have something that's three-dimensional and real. So here's an example of what you're seeing there as an illustration, where we've got powder that's being set on every single layer, and that's being fused and bonded until you have something that looks like this. Why is this an interesting shape? Well, it's got pores in it that actually get smaller as you get further into the object. There are nested voids in here. There's a structure to this element, and you can't imagine trying to drill something like this out of a block of metal. It would be certainly quite a challenge. I mean, imagine the number of different size drills you would need. And how do you really get in there to create stuff that looks like this? It's a challenge, and in fact, it's not actually possible. So 3D printing offers designers far greater freedom in terms of what they can achieve with a manufacturing technique. But with this new manufacturing method that allows for fairly complex structures, and we'll see a few more of these in a second, we need the right design tools now. So it was all well and good being able to sketch things on paper or draw things with straight lines, but actually we now need computer-aided design software that is tailored for this manufacturing method. Despite being perhaps a very free method, you can design it, you can create it. Well, that's not strictly the case. There are still limitations even in 3D printing or additive layer manufacturing. These largely lie in the way the manufacturing process occurs. We've got layers being stacked on top of each other. If you're working with metals, you need to have some kind of support in there so that overhanging beams can actually be constructed and not just fall and collapse in terms of the build. So we need software tools that allow for the design rules to be built in. So we can start with solid objects. Here we've got a very simple cuboid. We can use that as a design space or a design volume to create structures. Now, these structures in themselves have very interesting characteristics. And again, we've gone from solid to structure now. We can't really achieve structures like this if we use traditional manufacturing methods, but with 3D printing, it certainly is possible. We can alter the density of that structure using density functions. We refer to these as kernels in the industry. So these kernels can actually alter the density of the structure you see there, and we can even spell out the letters TED in this X topology structure. I'm not sure if you can see that. It's a wonderful event that happens in Bermuda, and I'm glad to be part of it. So moving on, so why structure? Why do I keep mentioning structure, and why did I mention solids before? Well, I have a big example of one of those here, and we'll just discuss this a bit more. Fundamentally, the reason I keep mentioning structure and solid is that structures are much lighter. They take a lot of the volume and waste material, we could say, out of what you need. So if this were to function in a certain way, does it really need to be fully solid? Why not just take away the solid volumes you don't need, or solid elements inside this you don't need, and just be left with the structure that's actually the functional part of what you need there? So here we have a number of examples of structures. We have the green one there that allows for a multi-directional support mechanism. Therefore, if it was restrained at the bottom and a load applied on the top, it would be able to sustain that load. And we can vary the density. If you looked at the one on the right to it, that's a less dense structure. Again, we can vary the density in such a way as to produce something that is more porous, perhaps in nature. The less dense structure will be a lot lighter in weight. But again, we can still tailor it to perform as needed. We've got the one on the bottom right, which is actually this one I have here. And I'm not sure if you can see that it's a fairly porous structure with a spherical profile inside it. This lends itself more into medical applications. When we think of cells growing inside scaffoldings or cells growing as part of perhaps a medical implant, let's say, where we could coat the medical implant with structures that look something like this, and that would encourage the bones to grow into them and create a better fusion. And I'll show you an example of something real in that context. And finally, we have an interesting blue topology there, which is actually a support mechanism mostly for footwear. It compresses down in a spring-like way, but once it's locked down, it doesn't have much lateral movement. That lends itself more into a footwear application where, for example, if you're running around and your heel hits the ground, you wouldn't want too much lateral movement, but you do want some cushioning. So that kind of idea works quite well in that context. Now, structure, again. We can take inspiration from nature. If we took a cross-section of a bone, we'd realize that it's not actually fully solid. In fact, Darcy Thompson, in his treatise titled On Growth and Form in 1917, described that the internal structure of bone is actually dependent on the genetic heritage of the individual, as well as the environment that he's exposed to. So a runner, for example, would have a very different internal bone structure as compared to someone that does a lot of heavy lifting. Dense bone is very heavy. Therefore, having void spaces and a structure that actually works, that gives a performance characteristic that's needed by the individual, is actually a win-win situation. The bone optimizes itself and grows and becomes this interesting structure, like we can see here, to support someone's weight in a specific way. This is the top of a femur bone. And you can see there's a very interesting line of networked trabecula inside that bone. That is because it sits just inside the hip socket. Therefore, the line going from the hip socket all the way down to the inside is quite dense, and that's because there's a lot of force acting in that specific direction. But as for the rest of it, you only get some network where there needs to be to provide some subliminal support. So in this case, we can take inspiration from nature, realize that creating void spaces and using internal structures to save on weight can actually be a very clever thing. And when we apply this to something in engineering, we can end up with very intriguing designs. Again, we can only work with structures because all of a sudden we have a way of creating them. There's no point dreaming these things up if you can't create them and make them real. Now, here we have an engine block, for example, solid metal, 2 holes at the top, 1 through the side, normally used to mix 2 fluids together. We can use 3D CAD software to create a very nice piping mechanism, create structural designs that actually support the piping mechanism and connect to the top and bottom of this engine block, and finally have a much denser network of organic-looking structure to allow for functional support. Now, those might be wonderful renderings, but I actually have the real piece here, made in stainless steel, again 3D printed, and does actually include all the intricate design work that's shown on screen there. So this is only, again, possible because we now have a new manufacturing method that can allow for these kind of intricate designs. Here's an example of a heat exchanger. All these wave-like forms inside this particular heat exchanger allow for air as it flows through to have a certain amount of turbulence, which means that it can then capture more heat from this metallic part. When used in a car, for example, we can end up with a far more interesting heat exchange mechanism which can cool the car down much faster, perhaps, than a standard radiator would. This is also a very modular design. We can take sections of it and then repeat them and fill any space that we would like to create and provide a heat exchange function with. Again, this is not a 3D rendering, this is a real picture. And it does demonstrate that, once again, with 3D printing, we can achieve these kind of designs and make them real. You can't imagine trying to machine something like this. It just isn't possible. So moving on, we have examples of medical implants. Now, I have them here. These are just some demo pieces. But you can see that they've got a coating of structure on top of them. And this is something I mentioned previously, where we can create structures that allow for what is known as osseointegration, or bone fusion with the particular metal implant. That particular structure there is actually something that looks more like real bone network, trabecular network. And once inserted into perhaps the hip, like this would be, or the tibia bone just down there, it would allow for those particular sections of the bone to fuse in with this implant and create a much better bond. Now, it is possible to make these kind of designs possible with other manufacturing methods, but through the use of 3D printing, you end up with something that is far more robust, simply because this is a single construction. This part was not coated with this particular network. It wasn't coated with this particular structure on top of it. It was built as one single piece, which means that when it's actually used in practice, it is a much stronger bond between the external and the internal metal, simply because it's the same part. So this is offering interesting possibilities, and it's a very new concept, perhaps, in terms of being able to create these kind of designs using a 3D or additive layer manufacturing process. And we can move on to footwear. And a high-heeled shoe, for example, I'm sure ladies would agree, causes a lot of pain. If you were to look at what happens normally in the ball of the foot, if you're standing in your high heels and you're raised up, the ball of your foot will experience a lot of pressure, and it's really the spikes of pressure for prolonged periods of time that cause pain. If we had a lattice or structural design which allowed for that pressure to be dissipated in the ball of the foot, therefore allowing for less spikes in pressure, well, then we suddenly end up with something that's a lot more comfortable to wear. So you can go to dinner, go to the dance, not have to walk away holding your high heels in your hands, but actually keep them on. So it's a very interesting application, and one that has certainly shown a lot of interest. If you'd like to know when this will be available, let me know. Moving to beyond structures, so we've looked at structures and the reasons why they create rather interesting and intriguing products. Well, here are everyday products, in a sense: pens, lemon squeezes, a range of lamps. I've actually got 2 pens here, 2 different designs, one done in plastic and one done in titanium. Now, both of these have such intricate design work to them that it's not really possible to create casts that can make this kind of design. You're not going to get a special drill or milling mechanism to make a pen that small and that intricate. Therefore, it's only possible, again, with 3D printing. We can see an example there of a chainmail system with a butterfly on it. Well, the butterfly outline is actually Swarovski crystals that are clipped on. So it's possible to print and make other products that go beyond what I've shown as structural designs, which are very functional. We can make everyday products with them. And it's a revolution that's happening now, where you can go online to certain websites, and they will allow you to actually upload your 3D CAD file, and people can then buy your 3D CAD file and download this and and have it manufactured, and there it is, their part. They can further customize this, put their name on it, and do more things, like even alter the shape of the design, as governed by the designer themselves. So it's a very powerful concept because it's now allowing for a more local production to occur. So we may have some software that allows for some local designer in Bermuda to create wonderful lamps in 3D using software that is readily available. And then being able to say, guys, I've now released some great artwork, some great lamps. Why not go and actually buy it off my website? And if you could buy it off my website, why not get it manufactured locally? If you had 3D printing bureaus based in Bermuda, it would mean that you're not going to have to ship parts from abroad that were custom-made for the individual. You could just, here's my wonderful cufflink. Oh, I didn't mention that, by the way. You can print cufflinks too. And I've got some here customized with my own initials on them. So it is possible to just pop into your local store. Yeah, I want to customize this cufflinks. I'd like to change the design slightly, a few clicks of the mouse, and there it is, and send it to my local 3D printing bureau. Perhaps they'll get to a stage where you have vending machines that have that are 3D printers, and you just put your USB stick, or perhaps you won't use USB sticks in those times, but you could just put something in, here's my file, click print, and in a couple of minutes, or maybe in 30 minutes, maybe an hour, maybe a few hours, who knows, you can then come back and pick up your new parts and take them and use them. So 3D printing is offering the world a very interesting and very compelling way of creating things, where we're able to now create stuff that we can begin to dream about, where we can go beyond what the restrictions are in terms of limited ways of building stuff, and actually look at, well, let's try and imagine this in software. Okay, now the software creates a 3D design. Now let's build it. Well, there it is. It's possible. So I'd say for Bermuda, get excited, get involved. This is a very interesting technology, and it's happening right now. Thank you.